Welcome to the week 2 lecture for QSO-600 Operations Management. This week, we plan on covering just a couple things. I'm going to cover location analysis techniques. I'm going to basically provide some information on a few of the ones that I've used, and just some background to help you understand if you plan on using these in your portfolio. I'm going to briefly talk about quality control versus quality assurance. I feel this is fairly important when you talk about operations because this can make the difference between apples and oranges per se. The quality control really defines the tempo of an operations control, quality control program. So I'm going to briefly go over that. And then I'm going to briefly go over the Taguchi loss function. I'm going to use this in context of the cost of poor quality to help people understand how poor quality is not a problem solely for the company, but as Taguchi would say, it's a loss to society as a whole. So these are the three things I'm going to focus on. And if anyone chimes in before the time I'm finished here, I'll be more than happy to answer questions. Right now, it's just myself. But if people come in, I'll be more than happy to answer some questions. So location analysis techniques. There are many ways to analyze, to make a decision on where to put a warehouse or a central location or where to move your central operations. I've probably counted dozens of these, but I'm going to basically cover generally how it works and a couple of the main ones that are used, that I've seen used. Make a note, note that usually more than one is used at one time. So like for instance, they may decide to use the center of gravity one to identify a general location, and they may fine tune it with a load factors analysis to say, okay, well, we may want to give it some real world analysis with it. So, and then I'm going to give you one that's more quantitative, which is they call this cost value, but actually you can actually use the one that I'm going to provide to determine almost any variables you want. Same with the other ones. So I will cover that when we get to those. So load factor rating is the one that's probably the most popular. And this, I've seen this a lot, used a lot with Six Sigma. They're really big on this to help people make decisions. It creates a score for each possible location, varying upon the criteria that the management or the decision makers, the stakeholders make. So this includes two things. Each criteria has a weighted score, which is assigned by management or the stakeholders to signify to the decision makers the importance of that factor. And weight's going to be ranked or as a percentage of all criteria, and I've seen both. For instance, if you have 7 criteria, you may have numbers 1 through 7. Subsequently, also, you can have, I forget what the exact name is, but you can actually amplify it. So for instance, you may double each of the rankings. So number 1 would be 1, number 2 would be 4, number 3 would be 6. Actually, well, yeah, 1 would be 2, then 4, then 6, then 8, then 10, then 12, and 14, and 16. All the way down to put more space between each of your levels. I have also, and I've seen this in Six Sigma run criteria analysis where they will actually square each of the ranks. So for instance, first place would be 1, second place would be 4, third place would be 9, fourth place would be 16, so that you get a more, it's a more multiplicative ranking for each criteria. And then for each of those criteria, then for each site, you will then on a scale of 1 to 100 or 1 to 1,000, I've seen sometimes on some scale, give it a grade. Sometimes I've seen people use this qualitatively with AMAs. Like for instance, one time we had delivery time or percentage of correct products correctly sent without defects. So these are they would try to qualitatively create the second criteria. So here's an example of basically a very basic load factor rating, and I basically chose four items: proximity to customer, proximity to supplier, labor costs, and transportation costs. I've seen these have as many as 10 or 15 criteria. It just depends. I usually, when I've done this with management, I usually ask for no more than 6 or 7, because after that, you start to get some really really weird weights. So, and this basically is from 1 to 100. Each of these is based upon 1 to 100. As you can tell here, the weights is as a percentage. So if you add all these up, it equals to 1.0, which is 100%. So for instance, transportation costs is considered 10% weight of the entire decision. Labor costs is 20%. Proximity to suppliers, 20%. Proximity to customers, 50%. Okay. So then, and actually, you know, I may not have, okay. I didn't go through this slide very well, so let me go ahead. So in general, you have 3 basic steps that you use in a location analysis. First thing is you identify the criteria. And in many cases, the criteria can be related to the functions. And what I've seen, what I recommend when I've done this myself, is I'll go to each function that has a stake in the decision and say, okay, what is most important to you? So let's say the person went to marketing and said, hey, what's important to you? The marketing professional might say, well, I need to make sure that we have the proximity to customers. This is very important to me. And then production, proximity to suppliers, because we want to make sure that we can get materials as quickly as possible from our suppliers. The distribution section of the company might say, well, we need to look at transportation costs to customers and accessibility. I'm going to post a week 10 assignment video that I made for my supply chain class that goes over this in very good detail, how they quantitatively analyze this for you to look at and watch to get some ideas for that. But that's if you decide to use supply chain. And assembly, the people who do the production work, they may say, well, we want to make sure that our production facility has access to a skilled workforce. So you may also have, like, you know, near a college or, you know, next to good schools. It just depends. So this gives you a good idea as to how you could create a criteria. And I've actually literally gone to that Deming diagram. I've made a Deming diagram for a company with each of the different sections. Sometimes you got 5 or 6 or 7, just depends on the product and how the company is designed. And just ask each of the people who manage those sections what's important. And eventually you'll make a list. And then with this list, I go to the main stakeholder, either the director or the president, whoever's the one that's asking for all this information, and say, okay, here's the criteria that I got from all the subsections. What do you think? What's most important to you? And then they will give this, then they will go back. Let me just go back to this here. So they will go back here and say, okay, well, I think proximity to customers 50%. Then I'll go back to the other people as a whole and say, hey, this is what the boss said. And this is how it's going to roll out. And I just do this so that if the guy says, well, yeah, he said that transportation cost is only 10%, but he may not remember a problem when we had a snowstorm or transportation costs skyrocketed. So then you say, hey, look, you know, so you just go back like one iteration and go back to the main decision maker just to clarify, to make sure that he understands the context of all the decisions. And then at that point, then you just have to find a way to rank all these, to give a score. In some instances, I've had all the stakeholders in the same room where they can get together and they give me this information. I've also seen where maybe it's quantitative. They may have some kind of information where they can quantitatively decide what this ranking is. So then now once you get this, the weight finish, and you get the score for each location, then what you do is you basically multiply the weight by the score to give you the weighted score. So in this box here, I basically take in 0.5 times 80, and this gives you 40. 0.2 times 50 gives you 10. You go all the way down and you add them all up, and voila. In this decision, site 1 scores significantly higher than the other 2. Now, be forewarned, this doesn't mean that you're going to absolutely build at site 1. What this means is that in case, I usually recommend to do more than just one type of these, especially like this one's very subjective, obviously, because especially if you don't use quantitative analysis to do your scores here, these can be very subjective. So I usually like to include this with a more quantitative analysis. Even something like a center of weight, which has some qualitative analysis inside it. So this is used as a means to kind of give some insight as to how the sites match up at the time. I've also used this within a quality function to help rank like reliability improvements. I've used this to help identify what location we are going to put a new repair facility in. So the location factor rating can be a reliability factor rating. It can be a design factor rating. Anytime that you want to make a weighted decision about a decision using 2 criteria. So, center of gravity method, and this is very simple. It's basically, it determines a weighted center to identify an optimum location. And what I mean by weighted center is, let's say you have 4 points and you triangulate. You basically draw an X between the 2 farthest top left, bottom right, and you draw a line between the top right and the bottom left, and then you find out where that pinpoint center is. You can also do it mathematically. So we basically do that, but what we do also is we use a second criteria, which in this case this is for transportation. So we're going to determine the best location to place a transportation facility based upon location and the weight shipped from the facility. In theory, you could use this for location and cost. If you want to locate a distribution center between 4 or 5 or 6 retailers, you might say, okay, well, let's do a weighted center of gravity to determine where we should put this distribution center as it relates to the profitability of each of the 5 locations. And the way it is done, you generally multiply your 2 criteria together. In this case, you would multiply the X coordinate by the weight of that location. And then you would do that for all of them, all the locations, 6, 7, 8 of them. And then you add them all together. Okay. And then you divide it by the sum of all the weights. I'm going to show you in a minute in the next slide. And then for Y, you do the same thing. You're going to take the Y coordinate of each of your locations, multiply it by the weight or the profitability, whatever this criteria that you use is. And then you're going to divide it by the sum of all the weights or all the profits or whatever you use for this criteria. And it would look something like this. So I didn't highlight the decision, but basically I've got 2 sites, and I've got basically location 14, 12, 10, 13, 6, 16, 8, 19. You can use a Cartesian map. You can use a general, any type of map where you can kind of make this, or you can make like a 2-dimensional measurement. And then all I did here, the center of gravity for X is 14 times 100 plus 10 times 100 times 6. I'm sorry, 14 times 100 plus 10 times 75 plus 6 times 125 plus 8 times 110 right here, divided by the number of locations. So you get an average of all the locations. Then when you do this, you divide it by all the weights added together. Okay. And then here you do the exact same thing for y, but and this time you use y. So 12 times 100 plus 13 times 75 plus 16 times 125 plus 19 times 110 divided by the number of sites. You add it all up, divided by 4 in this case because there's 4 sites. And then you add up all the weights, and then you take the top divided by the bottom, and that gives you your y location. In this case, the y location is 9 and 15, so it's right here. So this basically says that taking it into consideration, all of the sites, this is the best weighted location for the site. Now, I did not cover this, but there are some assumptions that we have to make. The main assumption is that all transportation is in a straight line. So it ignores things like toll roads or mountains or something that might interrupt the straight line. So that's the main assumption that it goes into. It also ignores density factors. Like for instance, if you've got like locations of high population, let's say this is a state map and you got things across state, you may have a big city on the left-hand side of the state that should weight it more. Now, the criteria may take that into consideration. All right, this is part 2. I'm using Camtasia to record now because Zoom is being a little bit finicky. So when we look at center of gravity model, we need to assume that all transportation in a straight line is as the crow flies. So what this means is we ignore density factors such as populations and suppliers, unless the criteria that we use takes that into consideration. Like for instance, in this example, we use weight shipped from the facility. That really does not take into consideration things like, for instance, you may have a lot of population in a certain area. In a way it would, I guess, because if you're in a location with a lot of customers, you do a lot of deliveries. But overall, your fidelity of your measurement may be lower because you just generally do not have a very accurate means of including such things as density factors. Or like for instance, if there's a big mountain in the way, you may have a density factor where the mountain doesn't consume anything, which may cause some bias in your selection. I have here that it's primarily for warehouses and distribution centers, but you can use center of gravity for pretty much any decision where you have to determine a weighted center based upon a physical location and a certain criteria, such as weight, profitability, etc. So I already showed you this. So now, location cost volume profit analysis is used to calculate changes in cost and volume for each location that you want to decide upon. Now, the assumptions are is that sales price, variable costs, and fixed costs are constant across all locations. And this is difficult to get through because you may have certain locations that might have different fixed and variable costs. It uses even measurements across all the sites. So all products made or sold, costs only affected by changes in activities. So if you change the activities related to a product, that would be reflected in your fixed and variable costs. And this is a major one that I've found for companies that do multiple lot sizes. All products are sold for the same price. So if you have different pricing for different types of customers, this is not going to be caught very well in this. So this is generally used to assess the viability of multiple site alternatives. So key calculations, you've got contribution margin, which basically is sales revenue minus all variable costs. You've got contribution margin ratio, which is basically the ratio of sales dollars to fixed costs. So it's contribution margin divided by profit or the sales, whatever you want to use. And the break-even point is level of sales where net income equals 0. And basically, it's your variable cost plus your total fixed costs. And also, it's also where your contribution margin equals your fixed costs. So your contribution margin is how much margin that site will make. And when that equals the fixed cost of that location, then that's the break-even point for that location. So I don't have an example to show on the screen here, but there are several examples on the internet, and I think the book has a good one. So I just wanted to generally cover that just to kind of show you how that's used. Now, quality control versus quality assurance. Um, I you always hear about a quality assurance department. You never really hear about a quality control department. I always hear about the quality division or quality assurance team, and quality control is very important. But in many cases, what I've seen is what a quality assurance team does. It does a quality control role. Quality assurance is more about a kind of like the theories and the methodologies. So quality control refers to how an organization fulfills quality requirements. So basically, it tells you basically how a company is going to ensure that the products have quality. So, for instance, I have here like inspections is a way to do it. Statistical quality control. Sometimes you hear it called statistical process control. It's pretty much the same thing. Um, and in general, what quality control does is it reviews the quality of all the factors associated with the production. So, if we look at an item that we're making, and let's say it's got 7 processes in line, we would, as a quality control function, we would look at those 7 locations and say, okay, where would be the best place to put in a quality control? Do we want to put it in at the end? Do we want to inspect it? Do we want to put in? Can we put statistical quality control where we get like automatic gathering of data related to the product in each of the 7 processes? Where are we going to? What tools and how are we going to gather this information? And that itself can be its own class because you got things like control charts, you've got scatter plots, and these scatter plots and control charts can use this information that you gather to develop a visual understanding of how your processes are in control. Now, quality assurance is generally it's focused on providing confidence that the quality requirements will be fulfilled. And this is basically a strategy for how you're going to do your quality. So as it says here, it focuses on how the process has been performed and how a product is made. So how do we build quality into our processes? How do we build quality into our culture? How do we build quality in anything that goes towards making a product? And the main tool used for quality assurance is auditing. So what we'll do is we'll audit a division or a department to see how well they are following our quality requirements, our quality strategy. So the audit may determine that certain departments within a certain operation may be following the quality strategy well. They may be following it very poorly. And these audits will provide recommendations on how to improve their ability to follow the quality strategy. And you've got things like quality management systems, and that's kind of a quality control function. But in many cases, a quality management system can have inside it implicitly the strategy behind how all these tools are used. So, quality control, general definition from the book, I believe, detects failures using testing techniques to identify product errors or flaws. Test products during specified intervals. Basically, once again, based upon the process, we're in the process that you want to measure. And it includes product requirements. Now, this can be very tricky because you've got customer requirements and you've got design requirements. Usually, the mindset is the design follows the customer requirements, and then the production follows the design. So in theory, we can test the production to see how well we followed the design. Then we can test the design to see how well we follow the customer criteria. We follow customer criteria by surveys or ways to get the customer to give us feedback. So we say, yeah, this design is liked, disliked. I'm going to try to put something together on that Kano model to help you understand how a product's features are accepted by a customer. We also have so then we could test the process, how we build on the design by saying, okay, this design has such and such tolerances, this has such and such requirements. How well does our production pipeline follow the design? Okay, and then it's a loop. So when the customer receives a product after it's gone through our system, many people find it hard to realize, but you can follow every step of the way, make a product exactly to design, and still have a product that the customer does not want. And it could be very well because we didn't listen well to the customer. Okay, you could listen very well to the customer and execute poorly on production, and therefore have a product that the customer may like, but it has poor quality. So it's an iterative loop where we keep going through the loop to make sure that our design follows the customer needs, that the production follows the design, and that as the product is sent to the customer, that it continues to provide value to the customer. So that's generally what quality control is supposed to do. Oops. Quality assurance. So with quality assurance, we continually check product quality through testing, inspections, process control, and we try to control and prevent flawed products from reaching later stages of the product development cycle. The goal of quality assurance is to catch the flawed product as early as possible so we don't keep spending money on a flawed product, and that's like wasting money. So, and it focuses on improving the quality, guaranteeing the quality of the system. Well, the Taguchi loss function is a good way to show the cost of poor quality by describing the loss in terms of a system. In this regards, the system is viewed not only from the corporation perspective, from that of society. Taguchi's original writings stated that any time a product deviated from optimum quality, there was a loss to society. And a general example of this is, let's say you purchase a car from a dealer and the car is of low quality. You will end up spending money and resources trying to fix the car that could have been gone to something else. When you read about Taguchi, you usually view it within the aspects of a corporation, such that if you spend money to correct a flawed part, that takes away from money that could have been done for something else that could have provided value to the customer. But just remember that Taguchi's original writings focused also on viewing the system to include society in general. So, as this slide says, it basically describes the losses that a system suffers when we have a loss of quality, when we move away from optimum. I'm going to show you a diagram in a minute that more explains how this works. And this is the main key of robust engineering, in which basically moves around designing statistical process controls into the design function to improve the design and the producibility of a product. And it assesses economic loss from a deviation in quality. He does have an equation for it. I'm not going to share it with you in this presentation because it's pretty lengthy. If you want, Taguchi has a book. I will provide the link if you want in class. That basically his book tells you all about the equation and how to figure it out. This is also part of the robust engineering process. So, as I mentioned earlier, it aids in understanding externality, which basically is a form of shifted burden in which we shift the cost of quality onto another entity. Within the corporate world, let's say that a supplier provides a low quality part. Within production, the company that produces the product may end up having to put money into getting that part to work. So that's money that's taken away from something else that would have made money for the company. So this is different than a traditional target thinking or tolerance thinking where loss of quality is instantaneous. Taguchi viewed loss as a slow decline and not based upon what we do. When we do yes, no, it's either good or bad. Within Taguchi's mindset, quality was a gradient that moves away from optimum. Okay, so here's the Taguchi loss function. And as you can see here, you have a an inversed parabola that goes up like this. And then down here you have a normal distribution. So this reverse parabola shows the loss of resources and money due to poor quality. Optimum quality is defined basically as the bottom of this trough here. So anytime that we move from the bottom, which is optimum quality, which by the way you'll never achieve, because variation occurs naturally in nature. You cannot remove all variation unless you have a very, very basic system. But for the most part, you'll never be able to remove all variation from a system. So basically, the further from the average you go, the more loss, which is measured on the y-axis here, the more loss you have to somebody in society. Now, this blue section here represents normal target thinking in a company, in which, let's say for instance that we are making a screw head with the dimensions of 3 to 7 millimeters. If the screw head is made less than 3 millimeters, you end up having to scrap the tool because you can't add on to it, obviously. And if you have it more than 7 millimeters once it's made, you have to send it for rework. Both of these represent the cost of quality, so to speak. Now, ideally, as we move down, you'll notice that if the screw is within 3.5, it may still be in tolerance, but it's not perfect. So in engineering, I always hear a thing called tolerance stacking, where in this example, let's say you have a screw that's 7 millimeters and a hole that's 3 millimeters. Even though both of those may be in tolerance, they won't be a perfect fit, or they won't be a tight fit. So this right here shows how tolerance stacking is kind of an erroneous idea, because it basically views variation as a 1 or a 0, or yes or no, or good or bad. Taguchi shows that it's actually a gradient. All right, so this is the end of the week 2 presentation. During the week, if you have any questions, even if it regards to this last week or the current week or even weeks coming up, please feel free to let me know, and I will either address them in the class in an announcement, or I will address them during the next video conference. I hope this has helped you understand the week 2 concepts of location planning and quality in general. Once again, if you have any questions, please feel free to bring them up in the classroom, and I'll be more than happy to bring them up. Until next time, I will see you then. Thank you.